Hello, we are Team 11, and we will be going into the analysis and the redesign of an electric scooter. Electric scooters are common last-mile transportation options, typically used in large cities, whether they be personally owned or rented. The current market is approximately 1 million units per year. Our team's focus will be on the electric scooter's rear wheel/motor assembly, which contains 21 parts plus fasteners, and the parts are manufactured using the mill, the lathe, injection molding, and other manufacturing processes.
Our primary customers are electric scooter rideshare companies such as Lime, Bird, Spin, etc., where they rent scooters to customers for short distance transportation. The scooter needs to be durable enough to last thousands of uses by riders of all experience levels, as well as be compact enough to be easily transported to and from charging stations. Our secondary customers are the individual consumers who purchase electric scooters to possibly replace bikes or other last mile transportation options. These consumers are more concerned about the price than the actual durability of the product. So through our functional analysis, we were able to determine that the task function of an electric scooter is to move your passenger with your primal basic functions, including accelerating your scooter and stopping your scooter. And notable basic functions include applying torque and restricting motion, while the notable supporting functions are protecting the motor, absorbing shock, and eliminating noise.
Thanks, Matt. So here I'll talk about our assembly sequence analysis. On the left is our first assembly sequence, which is our right to left method. For this assembly plan, we start with the right guard plate on its side and essentially stack and fasten all components in order, building up to the left guard plate. On the right is our second assembly sequence, which is our inside out method. For this assembly plan, we divide components into different subassemblies and put those together first. We start with the wheel subassembly, then move on to the motor subassembly, and then finish by enclosing both of these with the guard plates. Assembly sequence 2 is preferred because it's easier to put together different subassemblies than it would be to stack components up from one side to the next. This is our function component mapping matrix. Along the left side are the 21 different components of the rear wheel and motor assembly. Along the top are the terminal subfunctions from our FAST diagram, which include grip ground, supply power, convert energy, engage wheel, apply force, protect rider, protect motor, absorb shock, lower response time, and eliminate noise. Here are some of the notable trends from our function component mapping matrix. The right driven sprocket plate, driven sprocket, and driving sprocket all perform the same three functions. The three guard plates, as well as the fender, perform most of the same functions. In particular, they protect the motor and help eliminate noise. 12 of the 21 components help to eliminate noise, and 6 of the 21 components help protect the motor. Now I'll pass it on to Chris to talk about the bill of materials and cost estimation.
Here is the bill of materials for the rear drive unit of the electric scooter. As previously mentioned, it was assumed that the production volume is 1 million units. Additionally, the provided estimation equations along with an online cost estimator was used to calculate the cost per unit breakdown shown here. From these values, the total unit cost for the rear drive unit is estimated to be $204. From this analysis, it was found that the cost per unit could be significantly reduced by eliminating many of the parts used in this design through redesigning the marked components.
The functions were split between those that are required for both customer groups versus those that are required for just one. From here, the different parts were separated into platforms and modules. The modules specifically are the areas that would be changed between the different customer groups. Specifically, these include the motors and the sprockets. These will be changed because individual buyers may want a more powerful motor or different gearing so they can have higher speeds compared to the bike sharing or scooter sharing companies which want commonality and low cost. Multiple motor options are available for scooter customers. For the individual customers, they can buy the more powerful motor located on the left, and for the scooter sharing companies, they can buy the cheaper and smaller motor shown on the right. Between both these motors, they have common mounting as well as a common diameter to both fit into the scooter rear mechanism without any other major modifications. This also allows for differentiation of the product to best suit each individual customer's needs.
Another key item with these two different motors, as called out before, is the common interference between both of them on the attachment side. This allows for identical gears between the both of them and identical mounting plates as well. By doing this, we're able to delay our implementation of the different motors and have a similar assembly sequence much longer. In addition, the actual assembly is much easier since it's only the one process and not two. As you can see from the product family assembly diagram, we have pushed the implementation of the two different motors until item number 9. This is using assembly sequence number 2, or the inside-out assembly method. With assembly sequence number 1, or the right-to-left method, we introduce this variability at item number 2. By pushing it further downstream, we save a lot of cost and make the assembly sequence much more simpler. The main constraint into pushing the motor implementation even further down is just accessing attachment points and building the parts around the motor itself for safety.